Think forward. Think Research Channel.
The opinions expressed in the following program are strictly those of the speaker. They do not necessarily reflect the views of the National Science Foundation.
From the National Science Foundation, where discoveries begin. This is Frontier. Discussions of today's most exciting research subjects by distinguished scientists and engineers working at the frontiers of knowledge.
I am very honored and happy to have the chance to present this here at the National Science Foundation. This book is most of all an argument, and it's an argument about the present status and future direction of the field that I work in, which is fundamental theoretical physics. That is, and I want to be clear about this, that part of physics connected with discovering and uncovering what are the laws of nature. And so the issues that I want to talk about are in this domain, and I certainly don't want to be saying, and I'm not saying, that there is some big issue with the health of physics overall. Now, as an argument, and I hope the good reviews of the book have taken it and understood it as an argument, it invites discussion, and that's why I wrote it, to invite and suggest discussion about a number of questions which will become clear about the present status and future direction of physics. Now, I write from a particular situation. I mean, I'm a quantum field theorist trained in elementary particle physics, who's worked most of my life on quantum gravity, although I have also some work in cosmology, theoretical biology, some other subjects. And the concern that prompted the book is a concern that I know a number of my friends and colleagues have when we get together, and we think of ourselves roughly as the first generation of theorists trained since the Standard Model of elementary particle physics was established and written down in 1973. And the question is, have the hopes that we had at that time for post-Standard Model physics, that is basically what we were trained to do, which was continue the fast progress of physics, both theoretical and experimental, pushing our understanding of the laws of nature. Have we succeeded or have we not succeeded? And the test that I think we should be held to, and people in the future should be held to, is, have you solved the problems which were the major problems when you were an undergraduate student? So there are 5 questions which, with the exception of half of one of them, as you'll see, were key questions when I was an undergraduate student and graduate student in the 1970s. And I start with those, and then everything follows from that. So first, what I have often usually taken to be the key question for my work is how to unify or bring together the 2 strands of 20th century theory, general relativity, the theory of gravity, space, and time and cosmology, and quantum physics, the extraordinarily successful theory of everything else. A second question, which is a very interesting situation, that despite the fact that for contact with experiment and explanatory power, no theory in the history of physics has been more successful than quantum mechanics. Nonetheless, it has features that puzzled its founders, like Einstein and Schrödinger, and continues to puzzle and disquiet many people today. And these, I think, are issues that people will be familiar with. And they were unresolved 30-something years ago. In fact, they were unresolved 80 years ago, and they're unresolved now. The idea, and I want to separate this, there's the idea of finishing the revolution in physics that Einstein started, the transition from Newtonian physics to some new theory, of which general relativity and quantum theory and cosmology and quantum field theory and so forth are pieces of. There's that task which we must do, that is, we must have a single view, a single theory and framework for describing nature. There's another question which is sometimes confused with it, which is a question of unification factually. That is, it's either true or not true that the four forces we know about are different aspects of one phenomenon. We know it's true that electricity and magnetism are different aspects of one phenomenon. Are all the forces, four forces, different aspects of one phenomenon? That might be true, but it might not be true, but it's certainly a hope that many of us have had. And similarly, that all the different fundamental elementary particles, the fundamental fermions, quarks, and leptons, might be different states or different aspects of one fundamental entity. So that's the question of unification, of going beyond the partial unification in the Standard Model in 1973. Is there underlying nature, a complete unification of the forces and particles? Now, related to that is a fact which is, for many, the strongest piece of evidence that there is post-Standard Model physics to be discovered, and that's that the Standard Model, as successful as it's been, and in case people here don't know it or from other fields, since 1973, all experiments in elementary particle physics have confirmed detailed predictions of the Standard Model. The only adjustment that's been necessary is the discovery that neutrinos have mass. But nonetheless, this very successful theory has a feature which suggests there's something deeper behind it, which is that it has a lot of free parameters. It has at least 20, and with the neutrinos now having mass, maybe 29 free parameters which are input from experiment. These include the masses of the fundamental fermions, the strengths of the forces, and so forth. And the hopes for post-Standard Model physics since the early 70s have been to explain these parameters. Now, I remember a talk in about 1975 by Abraham Peiss in which he said, the Standard Model is wonderful, but not one mass of an elementary particle has ever been explained in the 20th century. That is, we started off not knowing why the electron has its mass, why the proton has its mass. We discovered the neutron. We didn't understand why it has the mass it's had. The same thing for the muon, etc. And Braun-Peiss emphasized that as important as it is to understand the dynamics of the fundamental particles in terms of gauge fields, there's something that he was very frustrated about, which is the ability to understand the values of masses and other such parameters. And 30-something years later, we still don't understand the values of any of those parameters. And finally, what is the dark matter and the dark energy? There was certainly good evidence for dark matter many years ago from the 30s, from Zwicky. Then Vera Rubin's studies with her students of galaxy rotation curves in, I think, late 60s and 70s, early 70s. Of course, we didn't know about the dark energy. That's the only new thing on this list. And we're in the interesting situation that we have a rather successful model of cosmology which depends on the parameterization of roughly 25 or 26% of the matter as dark matter, which means we don't know what it is. It's some sort of thermodynamically cold, unknown form of matter. And 70% is dark energy, which is some mysterious form of energy which has pressure roughly minus the energy density. So those are the 5 questions that we have been unable, although experimentalists have understood more and more related to those questions over the years, we theorists do not understand anything more about them than we did in 1974 and 1975. Okay. Now, is that a problem? Some people don't think it's a problem, and there are various reasons why you might think it's not a problem, like, well, it's harder to do the experiments, things are slower, things take more time. Others of us in the field are very frustrated and think it's a problem. I'm not a scholar or a historian, so I don't think I can judge that, but I was very impressed when I did a survey of the history of physics to try to understand for myself, is this a problem? And I was unable to find a similar period in the history of physics where 30 years went by without a fundamental deepening of our understanding of the fundamental laws of physics. Okay. Now, I do think it's a problem, and I have two hypotheses about the origin of the problem. Okay. And the purpose of the book and the talk is to make that argument for those hypotheses. You may in the end agree, you may disagree. Again, my major motivation is that I think we should be discussing this question. Okay. My discussion has to start with a few remarks about what science is. And I feel a little bit silly coming to the National Science Foundation. It's not silly to put this in a public talk, which is what this is taken from, but it's a little silly maybe to come to the National Science Foundation and tell you what I think science is. But I'll do it anyway because what I have to say here structures the rest of the argument. And the question is how do we go from the simple intuitive observations and discoveries we all make to science where we have by now a centuries-old tradition well institutionalized of making discoveries about nature. Now, there are graduate courses and undergraduate courses in the philosophy of science, and I have taught one such course. So there's a long discussion about apparently wrong explanations for science, how science works, and I'm just mentioning these just to give a direction to my own presentation. But the consensus among philosophers and historians of science at our present period is that there is no method that people follow that leads to truth. So science does not succeed because we adhere to a method. If that's so, why does it work? Why does it so undeniably work that we make discoveries about nature over and over and over again in diverse fields? And the conclusion that I've come to, which is not novel, there are historians and philosophers who advocate this, is that it works because we work inside of and form ourselves into communities that are tied together by some simple ethics. That is, there's not a method, but there is an ethics. And there are several different ways to say it. One of them is that there are two principles which govern the case when there is sufficient evidence to decide a question and when there is not sufficient evidence. And it's very simple. We argue from evidence. Science means we argue from publicly available evidence using standard rules of logic. And in some cases, the evidence suffices to decide a proposition or to strongly support a hypothesis. And when it does so, we must agree and say so. So there's this remarkable thing that sometimes we have controversy and disagreement in science, and sometimes we have consensus. And the consensus comes because we're forced to by the evidence. And when you become a scientist, you agree to be bound by that, even if you hate it, even if your own theories, even if the evidence goes against your own theories and your own hopes. The second principle is that to set up a situation where the first works over and over again, where sufficient evidence is gathered to gain consensus, you have to first have disagreement and even sometimes controversy. You have to accept that when well-trained people in the field look at the evidence and disagree about the implications, disagree about what theory they think is being supported, disagree about what direction they want to pursue to find an explanation, then we should welcome that diversity of views, and we should support it, because this is science, and nobody knows what the answer is. We wouldn't be doing research if we knew what the answer is. So what I have to say from now on, which is a specific case, is based on those two principles, and from them some simple things follow, which are also not special to science. When we face on the forefront of our knowledge some risky endeavor, we want to advance our understanding by a great amount. And there are different strategies and different ideas about how to do that by well-trained, good people. That diversity is good and not bad, because we don't know who's going to be right and who's going to be wrong. Okay. And as some of those philosophers and historians have argued and shown in detail, for example, Paul Feyerabend, the progress of science can be slowed down if we don't do that. That is, if we too easily come to agreement, consensus. Okay. So of those 5 problems, I want to focus on a particular one. I only have time for one of them here, which is quantum gravity. And 3 Roads to Quantum Gravity was the title of my second book, because the field of quantum gravity indeed is a major issue in physics to put together the pieces that Einstein and the other early 20th century physicists developed. A lot of work has been done on the problem. The problem certainly is not solved definitively. Definitively would mean you would gather enough evidence to convince everybody that such and such a thing is correct. And certainly in science, apart from mathematics, the basis of that evidence is always experiment. And I will be coming to talk about experiment in this domain. And a remarkable feature of the theory of this field is that there's indeed a lot of diversity of approaches. There are 3 broad approaches, which I'll be telling you about and contrasting the discoveries, achievements, and status of. I've been puzzled for a long time, why is there such a diversity? And this diversity expresses itself as different communities that hardly communicate with each other. And I've been troubled by that my whole career, because I'm the type who tends to migrate between different communities. And I finally understood, I think, why there is such a difference of viewpoints. And I think it's very deep. And it goes back to 2 of the 3 roads, goes back to an old and very fundamental disagreement in the history of philosophy about what space and time are, which is, after all, what the problem of quantum gravity is, to make a theory of what space and time are that fits consistently within quantum mechanics. In the 17th century, late 17th, early 18th century, there was a dispute between Newton, who thought of space and time as something that was fixed and absolute, and there was a conflicting view, which was actually the view of most people at that time, but championed by Leibniz, who was a great philosopher, mathematician, etc., the patron saint of computer science, modern logic, many other things. Space is an aspect of relationships between things, and time is an aspect of change in those relationships. And this fundamental split now goes under a different name. So just to introduce you to the terminology, in the old days, people called it the absolute versus the relational point of view of space and time. Now the absolute one is called background dependent, because that's a style of studying a physical system where you fix the geometry of space and time and have things move within that fixed geometry. And the background independent, when you treat the geometry of space and time as completely dynamical and with nothing fixed, as part of the dynamical degrees of freedom. Now, both of these roads have had important successes in the 20th century. The Newtonian way of looking at space and time, which is what most of us do and most of us teach in science, in physics, is the basis for how we formulate systems in quantum mechanics. It's the basis of how we formulate quantum field theory, which underlies the standard model of particle physics. The background independent point of view, however, is the basis of general relativity. So general relativity is, and this has been only fleshed out in detail since the late 1970s. That's Julian Barber, who was the person principally responsible for that, that we can understand in detail the interpretation of general relativity, what's an observable and so forth, and understand it clearly to be in the second point of view, in this Leibnizian tradition. Okay. Now then, it's not surprising that quantum gravity is hard and finishing the unification of physics is hard, because half of physics, this quantum field theory, the standard model, quantum mechanics, is formulated within one way of understanding space and time, and the other half, general relativity, is formulated on a quite different basis of understanding space and time. And since the 1930s, people have disagreed about which was more fundamental and what strategy to take to put these things together. Not only that, and I'm not a historian, I'm not a sociologist, and when I wrote this book, until the last version, there was going to be no sociology, no history, nothing about communities and science and so forth in it. But the editors kept saying to me, your story makes no sense. There's something behind your story. And here's the insight that I had. One reason this dispute over the right way to go about quantum gravity has been so hard to bridge is that they were embraced in the 20th century by different communities which use different styles of research. Roughly speaking, because any such thing has to be rough, there was a style of research that Einstein, Bohr, Schrödinger, and so forth carried out their discoveries of relativity and quantum mechanics, which was very individualistic, very influenced by philosophy. These were people who knew and were at home with the philosophical tradition. Okay? They worked in a style of research which was people sitting in their studies and arguing with each other and corresponding with each other. And they succeeded in making these revolutions in physics. Now, in the present day, there are people who still exemplify this style of research, for example, Roger Penrose and Alain Cohn, both great people, great mathematicians who also work in physics, and their names will come back. But this is not now the dominant style. The dominant style is a much more pragmatic, one could say even anti-philosophical style, certainly the style in which I was educated and trained in. It arose when people began fed up with people in the first style arguing about the philosophy of quantum mechanics and the meaning of it, and they said, let's just get on and do science. And in the 1930s, the people who came to dominate were people like Fermi, who didn't want to talk about philosophy. They wanted to understand the properties of materials or how stars work and things like that. They were much more pragmatic. And that is the style that became the dominant style in the United States, as exemplified by people like Schwinger and Feynman, Murray-Gell-Mann, and so forth. Okay? And that's the style in which I was educated. I was explicitly told, throw away your philosophy, don't think about the history of science. Okay? We have the standard model, just calculate and extend it. Now, this dispute goes way back. In the first paper in which Heisenberg and Pauli discussed correctly the quantization of the electromagnetic field, they also discussed the quantization of the gravitational field. That's not so well known. And they said quantization of the gravitational field, which appears to be necessary for physical reasons, may be carried out without any new difficulties by means of a formalism fully analogous to that shown here. That is the largest underestimation of the difficulty of a scientific problem I know about in the literature. It was a young Soviet physicist in Leningrad in 1935, Bronstein, who argued against his teachers and Pauli and Heisenberg, and said that the elimination of the logical inconsistencies requires rejection of our ordinary concepts of space and time, modifying them by some much deeper and non-evident concepts. So this split has been there from the beginning. Now, since the 1930s, there have been work along these two approaches. That is, take the first road, take quantum field theory and the tools of quantum field theory as developed for things in a background space-time and try to apply them to gravity. For example, if you can quantize electromagnetic waves and get photons, why can't you quantize gravitational waves and get gravitons? And the brief history of this approach has been lots of failure. Okay, my PhD was somewhere in here is one of the, and what I did for my first postdoc and what I did for my second postdoc is in the failure. There was a great discovery, which was Hawking radiation from black holes and related discoveries, Davies, Unruh, people like that. And then finally, there was a success with string theory in 1984, which I'll come to in a minute. The second road was even worse. Lots of failure. Okay, it's not, for example, known that Dirac, the great physicist Dirac, spent years and years and years on this, okay, in the 1950s and 1960s, as did other great people, without success. Okay. Finally, also in the 80s, in 1986, we had some success with loop quantum gravity, and then a variety of other approaches I'll be telling you about towards the end of the talk. Interestingly enough, there was one guiding idea which underlies the successes on both sides, that is string theory and what followed, and loop quantum gravity and what followed. And this is the idea that fundamental things are not points, they're extended one-dimensional objects. And in actual fact, this idea goes back to Faraday. So Faraday conceived of the electromagnetic field not as fields, but as lines of force, which he imagined were real things, were lines which stretched between charges and conveyed forces and between magnetic poles. Maxwell said, no, there really are fields. There's the little arrows at each point, and you integrate the fields and you get the field lines. But it turns out when you apply quantum theory to study a electromagnetic field or a gauge field theory, a Yang-Mills theory, which is an extension of that, which underlies the Standard Model, in the language of quantum states, there are phases of the system where this is the right description. For example, in a superconductor, the magnetic flux is quantized and comes in discrete lines. And in QCD, we believe that electric flux, to at least a certain approximation, is quantized. So the idea arose in the 1970s by people like Polyakov and Mandelstam, Holger-Nielsen. Let's deal with the fundamental forces directly by studying quantum mechanically the dynamics of these lines of forces. And that program carried out in the first point of view, where they were seen as moving in a space that already existed, became string theory, and carried out in the second point of view, where these were seen to be things whose relationships define space, became loop quantum gravity. So these two things are actually linked at the heart. Now, a little bit about string theory and its story and situation. String theory has certainly compelling features. It's a compelling idea that one really can achieve a unification of the different kinds of forces and particles we know about from vibrations of a closed string moving through space. One cannot capture the full idea of general relativity that requires that the geometry of space and time be fully dynamical with nothing fixed, but one can capture the properties of quantized gravitational waves as well as other forces. Okay. The technology involved is very similar to that we already understood from the Standard Model, so those of us like myself trained in elementary particle physics could rather easily learn it, to the third order of perturbation theory, which is a standard approximation procedure we're familiar with from particle physics. It gives finite and consistent answers, including a unification of the gravitational force with other forces. And certainly, whatever the fate of this as a hypothesis about fundamental physics, it's had useful applications both to mathematics and, for example, recently to heavy ion physics. There's an interesting application, which are both independent of whether it's fundamentally true. Now, unfortunately, there's a package deal. And what I mean by a package deal is what happens when you go to buy a car and you walk in and you say you want anti-lock brakes and a CD player, and they show you all these cars which have anti-lock brakes and a CD player and a sunroof and chrome magnesium wheels and racing stripes and leather seats and etc., cup warmers. Okay. And I say, I only want the CD player and the anti-lock brakes, and they say, it's a package deal, you have to get all of this. And I still don't know what chrome magnesium wheels are, but I have them. And so similarly, string theory came with some apparently non-negotiable extra features. That is, could only be made mathematically consistent so that it would have evidence of the different forces in it if there were 6 extra dimensions of space and there was an extra constraint on the dynamics, which we call supersymmetry. And the basic problem is that there's no evidence for either one of these. And in the history of ideas about unification in science, roughly speaking, there are three cases. There's the case where you unify something and there's something new that pops out that's right. That's like when Maxwell unified electricity and magnetism and got light out. Then there's the cases where something wrong comes out. You unify things that you know about together and something comes out which disagrees with observation. And we don't talk about those cases. And then there's a third case where there's a lot of flexibility and adjustable parameters so that there can either be wrong stuff or you can hide the wrong stuff. And this is an example like that, as I'll show you, which doesn't mean it's wrong. It might mean that the stuff that we don't observe now is hidden, yet to be observed. Okay. But that's the logical situation. So what about the story of the extra dimensions? This is not a new story. The idea that the unification of the forces requires extra dimensions goes back even before general relativity to 1914. And up till string theory, it always failed. And it failed for two reasons which trouble string theory as well. One of them is that you have to do something to hide the extra dimensions. The most common thing to do, although it's not the only thing to do, is to curl them up so they're much smaller than the wavelength of light or the probes we use, and then they can't be detected. The problem is that there's a great freedom in how you do that. There are an infinite number of ways to do that, consistent with there being 6 hidden dimensions and some assumptions about low energy physics and consistency of the equations of string theory. So that's the first problem. And as a result of that, it turns out that string theory makes no predictions for elementary particle physics so far. Roughly speaking, when you unify things, you have to explain why they're actually different. So why do different particles have different masses if they're all unified as vibrations of strings? They have different masses because they come from vibrations vibrating in different directions in these extra dimensions. And since you have freedom to choose the geometry of the extra dimensional space, you can make those masses to come out anything you like. The second trouble is that, and Einstein understood this, Einstein originally fell in love with this idea in 1919 when it was proposed for the second time of unification through higher dimensions. But already by 1923, he understood the weak point, and he wrote to a friend that either it's a unification or it's not. If it is a unification, then the extra dimensions are dynamical, just like the geometry of the 3 dimensions we know about. The universe can expand, there can be gravitational waves and black holes and so forth, and that should be true in the extra dimensions as well. Therefore, if they start off small, they don't have to stay small. They can expand, they can contract to black holes. There can be gravitational waves in the geometry of the extra dimensions, which would mean that the properties, the masses, and the charges of the elementary particles would oscillate in time. And none of that is observed. Or it's not a unification. You just fix by hand the geometry of the extra dimensions to be something fixed and frozen, in which case you're not doing something compatible with general relativity. The story with supersymmetry is similar. Supersymmetry, by the way, as is extra dimensions, both of these are hypotheses which exist outside of string theory, existed prior to string theory. Some aspects of them in some models are testable in the LHC, so which is an important thing to emphasize. But as it applies to string theory, supersymmetry has consequences which are not observed and which must be hidden by some mechanism of breaking or spontaneous symmetry breaking. For example, supersymmetry implies that the dark energy, if it exists, must be negative. It must be 0 or negative, or the so-called cosmological constant. And it was a big problem for those of us in the field when in 1998 the astronomers observed evidence for positive dark energy. So supersymmetry may or may not be observed in the LHC. Whether it is observed or not provides evidence neither for nor against string theory, because the models by which the standard model extends to include supersymmetry have so many parameters in them which match onto the vast number of different string theories that the extra particles that supersymmetry requires could have a large array of different masses and coupling strengths, and there's no unique prediction that what properties they'll be seen with, or indeed that they be seen at all in the LHC or any other experiment. Okay. So it took a long time for us, I speak as a group or a community, to really accept the idea that this was the case, this was the situation. That is, that the theory, to the extent we understood it, came in so many versions that it would make no predictions for future experiments. At first, there was a strong belief that the theory is unique. Then there was an understanding the next year that there would be hundreds of thousands of so-called Calabi-Yau manifolds by which the dimensions could be curled up. Then the year later, there was a paper by Andy Strominger, who was a professor at Harvard and a prominent string theorist, whose conclusions, however, were ignored by most people because he found there would be vastly more versions of string theory, so much so that he worried that all predictive power seems to have been lost. So this is an old issue. It was ignored. Some of us, this was what my first book was about, tried to reason our way out of it and deal with it, but most of the field hoped that the problem would be solved and would go away and there would be a unique version until 1998, when there was the crisis with the dark energy. Overcoming that crisis, that is making string theories that could accept a positive value of the dark energy, that was done in a way that made it clear that we were facing a vast number of different theories. And that brought on the present, what's called the crisis of the landscape. The landscape is a word that I originally used and that we use now to refer to the sort of the vast numbers of different theories. We see them arrayed out on a landscape. This is just a sort of summary of the situation, which is confusing and which people disagree about. What was compelling about string theory originally is still compelling. But there have yet to be any predictions. There's no strategy or sign of getting predictions from the theory. We don't know what principles the theory is based on. We don't have a simple, cogent mathematical expression of the theory. We have a vast number of different approximate descriptions of different cases. Okay. Now, in light of the concession that there would be, or the understanding, the agreement that there was a vast number of string theories, some string theorists began talking about what they call the anthropic principle, which is also an old idea, very well thought through by cosmologists, astronomers, and some philosophers, and pretty well discredited, in my view, already by then. The idea is that there's a vast number of universes within which the different geometries that give rise to the different string theories are chosen randomly, and in only a small number of them could there be conditions necessary for life, for example, a large number of stable nuclei in long-lived stars, and we live in one of those. And any predictions that you could make would, since there's a random population of theories in universes, the only predictions one could make would be features of our universe that were consequences of the existence of intelligent life. And that doesn't go anywhere. In the light of that, several people made a play to change the rules by which science functions. And in some sense, if my book is controversial, it's not the book itself, it's that it addresses a controversy that already existed, for example, in the book of Leonard Susskind and recent writings of Steve Weinberg or Joe Polchinski. These are very, very good scientists. And they began to claim that string theory was compelling enough that it should be considered the candidate for the true theory and the most likely candidate, in spite of the fact that it makes no predictions by which it might be verified or falsified. And these are some quotes by Steve Weinberg and Lenny Susskind. Weinberg's is long, but he talks about changing the definition of science in light of this fact. Sometimes there are revolutions in science, and sometimes there are revolutions in our conception of what science is and how it works. Lenny Susskind, who's somebody who's been a role model all my life, says it would be this was in an interview in Nature last year, it would be very foolish to throw away the right answer on the basis that it doesn't conform to some criteria for what science is or isn't. It should be emphasized that this is not a uniformity of views. Brian Greene said, you have to emphasize that I've always said, I can't do Brian quite, but you can imagine him. I've always said that there must be falsifiable predictions. And indeed, you go back to his books, and he does say there is no way to establish any theory without subjecting its predictions to experimental verification. Or Jim Gates, who many people will know here, a professor at Maryland, said on Brian's program, no one should believe string theory till it makes predictions that are verified in the laboratory. So that's the conflict over the landscape. Now, the philosophers and historians of science often say that you can't just judge one theory. You have to consider the different competing theories. Okay. So what about, I said there were three roads, and I told you about one of the other two, which is the Leibnizian-inspired, general relativity-inspired, relational or background-independent road. So I want to tell you briefly what's been happening on that road to give you a full picture of the situation, and then a little bit about the third road, and then how to resolve these issues. So actually, there's been a lot of progress on the second road, and I'm just going to give you a survey just so you get some ideas, some names, some pictures in your mind. If you do not think of space and time as pre-existing as a geometry that things move in, you have to represent them as some fundamental quantum structure, that is in terms of Hilbert spaces, states, and operators. And all these approaches I'm going to speak of do that. Then the question is, how do you get geometry back from a fundamental quantum mechanical language? And that's the problem of how do you get the low energy behavior or the emergent behavior, these are words we use, of general relativity of the world existing in classical geometry back. That's the key problem. The most successful research program is something with an ugly name of causal dynamical triangulations, invented by Renato Lowell in Utrecht and carried on with Jan Omborn and other people. And they basically make like an Ising model of quantum geometry. And imagine, it's a Buckminster-Fuller kind of thing. They imagine that quantum geometry is made of little discrete elements like triangles that are stuck together randomly, and they're quantum amplitudes for how they evolve. And they show under very general conditions in a class of these models that you get something that looks like 3 dimensions of space and 1 dimension of time out of. This has worked the last 2-3 years. What about experiment? Some people took a road of not trying to make a microscopic model, but trying to ask, where would the fact that the world is fundamentally quantum mechanical and space also is fundamentally quantum mechanical, where would this put a limitation on our present principles in a way that experiment could probe? And the most successful of these approaches is called doubly special relativity. These are 3 of the founders who founded it from different directions. Emiliano Camelia from Italy, João Maguejo from London, and Sabine Hossenfelder from Frankfurt. And let me tell you what this is, because it makes real predictions for upcoming experiments. So many people here will know special relativity, or at least know of it. There are 2 principles. Velocity is purely relative, and there is a universal speed that all observers agree on, the speed of light. Here's the modification. There is a universal speed that all observers agree on. However, it's only the speed of very low energy, very red photons. And there is a universal length all observers agree on, which is the so-called Planck length. This is a length given by, the square of it is given by Planck's constant, Newton's constant, over the speed of light cubed. And this is the length scale at which all the different approaches to quantum gravity agree new phenomena should become manifest at. It's 20 powers of 10 smaller than an atomic nuclei, unfortunately. But I'll come to that. Okay. And there's a fundamental paradox of if there's a fundamental length which is a threshold for new phenomenon, why isn't that incompatible with special relativity, which says that lengths are observer-dependent and transform? And the modification proposed of special relativity is to play the trick twice. That's why it's doubly special relativity. And say there's also a universal length, and it's that length where the new features of the geometry of space manifest themselves. And it turns out that that has a direct implication, which is testable, as I'll tell you in a few minutes, that the speed of light is not constant. It increases with energy in an amount proportional to the Planck length times the energy of the photon or neutrino. Okay, now back to microscopic models. The first one was just put together by hand to make a simple model. It turns out that actually you can put the equations of general relativity together with the equations of quantum mechanics and derive a unique and consistent mathematical theory from it. I emphasize mathematical theory. And this is loop quantum gravity. And it is a long story by now, since 1986. What we know is that this theory is finite. It has no ultraviolet infinities. We know as of 2003 there's a powerful uniqueness theorem that this is the only way to quantize a gauge theory with the symmetries of general relativity. And the key step here was taken by Abai Ashtekar, who showed that general relativity could be seen as a gauge theory. There's much recent work. We know that the theory has gravitons in it from recent work from Marseille the last 2 years. We know it has the Newtonian gravitational force in it. We know it gets black hole and cosmological horizons right. We know it gets Hawking radiation right with corrections. Does this predict DSR? This is a key experimental question because, as I'll tell you in a little bit, DSR is testable, doubly special relativity. I wish I could tell you it does. What I can tell you is that in a solvable model where the world has only 2 dimensions of space, which, however, could not be solved by any other techniques, with matter in it, it does predict this modification of special relativity. And we have semi-classical arguments, but not proofs. There's also an interesting area of interdisciplinary work in quantum gravity. So it turns out that there's been a lot of development the last 5 years in quantum information theory connected with the efforts to make a quantum computer. And it turns out that some people have found that work very useful because the problem of understanding quantum theory with dynamical degrees of freedom but no space, no classical description, is similar to the problem of trying to understand what would be going on in a quantum computer deep in the Hilbert space, in a region of Hilbert space protected by noise that would decohere the quantum bits of information. And here are 2 people who have built on that analogy, Fotini Markopoulou and Seth Lloyd, and there are real results that have come out of this crossover between quantum information theory and quantum gravity. For example, we always thought that loop quantum gravity was a theory just of gravity and space-time, and we would deal with matter later, maybe by connecting it to string theory. But Fotini and colleagues, David Krebs, have shown that actually the theory has matter in it, using the same technique that people use to describe what are called topological quantum computers. So we're very excited about that. There are also, it turns out to be a lot of input, well, some input from a few condensed matter theorists, because they see the problem of how geometry and classical physics in space emerges from a fundamental theory of quantum gravity as analogous to problems they're very familiar with, in which there's a discrete system in condensed matter physics and they're concerned with the phases of the material and how they emerge at long distances. And there's very interesting work by a number of different condensed matter theorists. For example, this is Wen at MIT, Olaf Dreyer at Imperial College, on quantum gravity. And finally, the last of the survey is an idea from Alain Cohn, who's one of the great living mathematicians, if not the great living mathematician in Paris. And Alain Cohn has a proposal for unification of the notion of geometry and the notions of quantum theory at the deepest level of their mathematical structure, that is geometry and algebra. Okay. And interestingly enough, the simplest non-trivial example of what he calls non-commutative geometry has the Weinberg-Salam model of electroweak interactions in it. And this is very well regarded in France. There are groups of people who work on this in France. Okay. That was the second road. The message is there's a variety of approaches. There's a lot of recent progress. on the second road. What about the third road, which I haven't told you about yet? The third road is a few people who say all you guys and girls are crazy, okay? Because quantum mechanics doesn't make any sense. And if quantum mechanics doesn't make any sense, it must be replaced by a more fundamental theory, and that's the theory that you should unify with gravity. And these people perhaps could be and should be easily ignored, except that they're named Roger Penrose, Gerard Etoff, Steve Adler, and a number of other of the most brilliant and successful scientists we know. However, if they're right, we've been all wasting our time. Now, how do you tell if we've been wasting our time? And this is what I'm going to wind up with. Well, this is science, right? And how you tell if you're wasting time as a theorist is experiment. Okay. Now, I told you that new quantum gravity effects are expected to happen at this Planck length of 20 orders of magnitude smaller than the atomic nucleus. So many of us have thought that experimental probe of these theories was impossible. And we used to say, and a few people who haven't gotten the message still say, okay, an accelerator powerful enough to study this regime of quantum gravity, the so-called Planckian regime, would have to be as large as the entire galaxy. Okay. And therefore, I think, and I used to believe this, and I think that a lot of us felt free to speculate outside of the realm of discipline from experiment. Okay. However, this turned out to be just wrong. Not that it wouldn't be useful to have an accelerator the size of the galaxy if NSF wants to go for it. But there are people who asked me to put that in. But that, as often happens in history, human ingenuity can find ways around things like that. And in this case, there was, for example, I've mentioned Giovanni Emiliano Camelia, a young guy, Italian physicist, who said to himself, there just has to be a way to probe that scale. There has to be a way to amplify physical effects. In proton decay, we figured out how to amplify physical effects only 4 or 5 orders of magnitude from the Planck scale to observable phenomena. There has to be a way to do that. And then he realized that, of course there is, because we have access every day to experiments much bigger than galaxies, which is the whole universe. That is, our astronomer and astrophysicist friends regularly detect cosmic rays and photons that come from cosmological scales. And those photons, as they travel, and cosmic ray protons, as they travel, are doing experiments. We just have to be clever enough to interpret them, to detect them and interpret them. So, for example, if the speed of light increases with energy, might it? Well, there are two cases. If special relativity just breaks down, then there's an effect which is parity odd. And that turns out to make planes of polarization rotate. And that's already ruled out by observations of polarized radio galaxies to 4 orders of magnitude below this inaccessible Planck scale. But in the theory I told you about doubly special relativity, the effect is parity even and is not yet ruled out. However, will be ruled out by the glassed satellite if it's successful, because the effect is, as I said before, of order the ratio of the energy of the Planck energy, which is tiny for gamma rays. But the effect amplifies if you have 2 photons going slightly different speed, one redder going slower and one bluer going faster. Over 10 billion years, that adds up to about 1,000th of a second for gamma rays. And that's easily resolvable by electronics that people are building into their satellites for other reasons. So the glass satellite, which launches roughly a year from now, will do this experiment and will be able to put limits on, or even detect this at the Planck scale. Similarly, it turns out that cosmic ray protons at the scales presently observed, that is 10 to the 19 to 20 electron volts, are doing an experiment in special relativity and its modifications all the time because they interact with the cosmic microwave background, and there are thresholds that are predicted to be in certain places from special relativity that result in changes in cutoffs in the spectrum that A, are seeable by current experiments, and B, test these quantum gravity theories because of the modifications they predict for special relativity. And there are conflicting claims from existing experiments in Auger going on now in Argentina. A cosmic ray detector will resolve this question. So there's no reason to give up on science. There's no reason for us to be having a discussion about changing the rules of science or having exotic strategies which don't involve experiments. Science is going ahead the old-fashioned way, and within several years, if it's Auger, maybe even within a year, if it's glass, within 2 to 3 years, we could see the announcement of modifications of the special theory of relativity from effects at the Planck scale, which will be testing quantum theories of gravity. So thank you.